Hey folks, welcome back. We're talking about dynamics. We are revisiting a problem that we did a few videos ago, the crankshaft problem, and we'll talk about that in a second, but what we're going to do is we're going to solve it in a different way. And I'm sure you noticed from the introductory video for this block that there are two ways to solve these kinds of general plane motion problems. So let's see. Let's start with our example situation where we have two blocks that are connected by some rod like this, and we'll call them A and B. Call this A, call this B, and hopefully you can see that. My pen is a little weak. It's trying to give up on me. So let me see if I can fill this in a little better. All right. Oh, there we go. That's lots better. All right. So we have this situation, right? And so B is going this way. V is going down. These are orthogonal, right? So I guess I could put that in, and we have the L and the angle, right? So let's just say that we have this angle is alpha, right? So the way that we've been doing it is what's called the relative motion method, and in general what we do is we if we have the velocity of A, right, so if we know VA and we want VB, then what we do is we diagram it. We say, okay, well, this is VA, this is VB, and VB is a composite of VA, right, plus the rotation of B about A, right? So the velocity of B with respect to A, right? And so this is VA here, right? And this gives us our formula, and it gives us a velocity triangle, this guy here, right? VB, VA, VB with respect to A. Great method. And then we solve the triangle, and then we can use the this equation and the equation that relates linear velocity to angular velocity and solve our system, right? That is the relative motion approach. That's the relative motion strategy, if you will, method. So in the instantaneous center of rotation, what we do is we say, well, V, say A with respect to B, is equal to omega AB crossed with AB, right? And so the cross implies an orthogonal relationship, and what we can do is we can expand this definition and just generalize it to say that V equals omega cross R, right? And since the bar, right, the bar between them is rotating at the same angular velocity anywhere along the bar, then it doesn't matter where the R is as long as it's orthogonal, right? So what we can do is we can say, well, let's start with vectors that are orthogonal to these velocities. We'll call this point C, and from here then we can apply this relationship specifically to our system, and what we'll say is VB is equal to omega AB crossed with BC or CB, right? CB makes more sense with CB, right? And that gives us omega AB is equal to VB over CB, right? And similarly, it's also equal to VA over AC, right? So in this situation, if we just solve for the VA version of this, then it's VA over, what is this? If we have the alpha variable here, then it's just L, that would be cosine. Is that right? So if it's here, then it's here, right? So then this would be alpha as well. So then it would be L sine alpha. Right? So if we know these angles, then we can solve this very quickly. And that is the, I guess, the overarching ideas behind this approach. There's a second nuance about this particular strategy, and we'll see that in the next video. But for the time being, let's revisit this problem that we looked at a few videos ago with the crankshaft, and just recall that we got some values, right? We calculated beta to be 13.95 degrees. We found that the solution was that omega BD is rotating anti-clockwise at 62, it's not 62 degrees, it's 62 radians per second. So R over S. VD was 523.4 inches per second along the horizontal, and VB was 628.32. So we'll draw our bar BD, right? And recall that this is beta. The whole thing is 8. Our velocity, our direction here is like this, and our direction here was like this, right? So first things first, let's draw in from the corners. I'm going to try to make it orthogonal to this guy here, and a dotted line because it is a construct, and hopefully my art skills aren't too bad. There we go. Okay, so we'll call this point C, right? And if this is horizontal, if VD here, if V sub D is horizontal, then this is vertical. And if we know that beta is 13.95 degrees, then that makes this angle right here 76.05, right? 76.05 degrees. That should sound pretty familiar. Also, we were given that, let's see if I can draw this here. So this is orthogonal, and from the problem statement we're given that this angle is 40, which means that let's see, if this angle is 40, then the angle inside of here should be 50, right? And if that's the case, then it should be pretty quick to, wait, hold on. That's not right. I'm trying to tell you lies. So if this is 40, check it out. This is cool. Then this is 40 here, right? And this is beta, right? Which makes the big angle here just 40 plus beta, right? So this is 53.95, right? Yeah. And if we add these two together, then let's see, that is 77, so 120, 130, which means that this angle right here is 50. Okay, cool. All right, and we've got that. So now we can get the lengths. Let's see, this, what do we call this point? This is B. So BC, this is D. So we can get this relationship between the lengths, right? We can use the law of sines for that. That's straightforward. So what would we say? We would say BC over, the opposite is this, so the sine of 76.05 is equal to 8 over the sine of 50, okay, is equal to, what's left, CD. Okay, so CD over the sine of 53.95. Okay, and we can use this to calculate these lengths, right? So we'll just preemptively do it. I don't even know if we're going to need it, but let's do it anyway. So BC is what? BC is the sine of 76.05 over the sine of 50 times 8, right? So let's see. 8 times the sine of 76.05 divided by the sine of 50. Okay, and that gives us 10 point, I'm looking at 352 inches. Okay, and go ahead and do CD while I'm here, because that I can get from just changing some numbers that are already on the line in the calculator. So that's 53.95. Okay, let's see, 53.95. 8.4434. Let's see, 8.4434 inches. Okay, so let's see. We need to calculate omega BD, right? And so what is that looking like? So let's say VB, since we've already got VB, we can use that. So VB is equal to omega BD crossed with the length BC, right? Okay, sweet. So then omega BD is equal to VB is 628.32, and let's write this longhand. So VB over BC is 628.32 divided by BC is 10.1352. I can already tell that's going to be about 62, right? So let's see, 628.32 divided by 10.1352 is equal to, I get, do I have that right? Wait, I did not, okay. Sorry, I punched a single digit in wrong. I'm like, wait, that didn't come out right at all. So I get 61.9938, which is exactly what I got last time. So 62, not degrees, rads per second. Okay, and it is in the positive direction, and previously we were talking about this, and it is in the same, and we could just look at it, right? So if this is going this way, this is going this way, then the bar is definitely rotating in the anti-clockwise direction, which is what we call positive. So we're good there, all right? And that is omega BD, okay? All right, so now we just solve the other one, and VD, so VD, which is the other thing that we want, is, put a line there, omega BD, which we now have, crossed with CD, right? And since this is on the plane and orthogonal, then we don't need to use components, and what is that? That is 61.9938 times 8.4434. So V sub D is equal to, let's find out, 61.9938 times 8.4434, and I get 523.4, that'll be inches per second, and that is in this direction, and that matches what we got up there. So you tell me. I think it's faster. I think it's easier. It works with velocity, not so well with acceleration, but there you go. This is the crankshaft example using the instantaneous center of rotation approach, and I hope that was helpful, and I will see you in the next video.